Okay guys, so today we're going to talk about when a derivative fails to exist. So you should be taking these notes on page 42, I believe, of your notebook is where this worksheet is. If you don't have it, look on binder paper, grab it from a friend, or you can grab it from the AP Calculus file on the counter. It should be in there probably towards the back. So take a minute, pause the video, and answer this question. What is the definition of a derivative? So I'm assuming that most of you said the definition of a derivative is either the instantaneous rate of change, or the slope of the tangent line, or maybe a function that tells you the slopes of every possible slope of tangent lines to a curve. But that's actually not the definition. That's what a derivative is. Like, that's its physical meaning. The definition of a derivative is that limit formula. Whoa. The definition of a derivative is that limit formula. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's actually how it's defined. So in order for a derivative to exist, the limit must exist, right? If you don't have a limit, then you can't have a derivative. That's the definition. So just to review, we say that the limit of some function, so I don't know, let's say x is approaching b, of your function exists when the limit from the left of your function equals the limit from the right. Whoops, that should be a b. Of that same function, right? The left-handed limit has to equal the right-handed limit. We've talked about that a lot, especially last chapter. So what that means is then, going back to this definition of a derivative, if the limit from the left does not equal the limit from the right, you do not have a derivative. You can't find a derivative at that point. So I actually want to look first with you at example 2. So example 2 is actually the piecewise function f of x, where f is for x squared, when x is less than 0, less than or equal to 0, and x plus 2 when x is greater than 0. So this is your closed circle down here, and this is your open circle. So if we look at this piecewise function, I know that you know this limit does not exist at 0. Right, that should be a 0. I'm not circling 1. So the limit from the left side of my function does not equal the limit from the right side of my function. So we know that the limit as x approaches 0 from the left of your function equals 0, but the limit as x approaches 0 from the right of your function is equal to 2. Okay, so and we can see that from our graph, obviously. So because this is happening, we would say that f prime of x does not exist at x equals 0. We can't find a function where we can't take a limit. Okay? Not only that, if we were to look at our derivative rules, so we were going to actually find f prime of x. So this is my function. I'm sick of these colors. Let's get something bright. There we go. So this is our function, and we're going to take the derivative of it now. So we're going to take the derivative using our shortcuts like we always did. So our top function is going to become 2x when x is less than or equal to 0. Keep your domain. And the bottom one is just going to become 1 when x is greater than 0. So at 0 then, f prime of x is going to equal 0, right, if I plug it into 2x. But then it's also going to equal 1. And obviously, like, 0 does not equal 1. Those two things are not true. So whenever you have a jump discontinuity, so in this case, we would say our limit does not exist, which means then that our derivative does not exist. If you can't find a limit, you can't take the derivative, and that's all based on this function or this definition right here. Okay, again, if you can't take the limit, meaning the limit from the left does not equal the limit from the right, you in no way can take the derivative. Okay, so that's the first time your derivative doesn't exist. So there's actually 2 other times. So the next time that your derivative doesn't exist is whenever you have a sharp point in your graph. Okay, and it doesn't necessarily have so much to do with the limit as much as it actually has to do with the tangent line. So let's look at example 1. So example 1 is absolute value of x. That's this curve, or this function, if you look at it. And what's happening here is going back to that idea of the derivative telling you the slope of the tangent line. But at this curve, at x equals 0, you could have a tangent line that looks like this. But you could also have a tangent line, well, that's not really tangent, but it could be tangent and look like that. It could be tangent and look like that. It could look like that. It could look like that. Like, we have so many tangent lines that happen right here. Like, imagine taking your pencil and moving it up and down or side to side. You don't know exactly where the tangent falls. There's not enough information given by the rest of what's happening, right? Even though we can predict the limit there, we can't necessarily predict what's happening to the slope of our tangent line there. The slope is changing so abruptly that we can't really figure out what's happening. It's going from a constant negative slope to a constant positive slope. So for example, like my slope for this line is -1. My slope for this line is +1. And at that cusp, or that corner, sometimes you'll hear it called, your slope or your rate of change is changing so rapidly, changing in such a quick instant with no pattern to it, you can't figure out what the definition of a tangent line is, or the slope of a tangent line, not the definition of a tangent line. So in that case, we say whenever we have a corner or a cusp, and it's always your book refers to them as corners and cusps, but we're actually just going to refer them as cusps. So cusps cause f prime of x to not exist. Okay, so in this situation, f prime of 0 does not exist because that's where my cusp occurs. However, I still have like a tangent line here, right? I still have a constant rate of change that's happening. I can figure out the instantaneous rate of change. So even though I don't have a derivative at this one point, right, where x equals 0, that doesn't mean I can't have derivatives elsewhere. Okay, so think about a function, right? Derivative's a function. You can have points on a function where it's undefined, or for example, this would cause a hole in your function, or maybe a jump in your function actually. Okay, so having a derivative not exist causes a discontinuity in the derivative function. I'd write that down. Having a derivative that doesn't exist causes a discontinuity in the derivative function. Okay, so now let's look at example 3. So example 3 is actually the cube root of x. That's the function you're looking at right now. And the cube root of x has a really weird situation in it. So even though the cube root of x is a function everywhere, okay, it's absolutely a function. It is defined everywhere. We're good. What's actually happening at x equals 0 is we have a vertical, sorry, my dog's making weird noises. We have a vertical tangent line. But a derivative is a function. Vertical lines are not functions. So if you have a graph that causes a vertical tangent line, at that point, you don't have a derivative. Okay, so in this case, again, we'd say f prime, ow, my dog just bit me. Bella, no. We'd say f prime of 0. I don't know why I'm putting an equal sign. It doesn't equal anything. It does not exist. F prime, I'm distracted because my dog just bit me. Jeez Louise, brat. Okay, so f prime of 0 does not exist there. Whenever you have a vertical tangent line, it doesn't exist. Because obviously a derivative is a function, and vertical lines are not functions. So when that's occurring, it doesn't exist. Not only that, a vertical line has undefined slope. The derivative is the slope of the tangent line. So if the slope's undefined, the derivative is also undefined. Okay, so those are the 3 situations, and they're pretty much the only 3 situations you'll see where you don't have a derivative. So the first one, again, is if you have a cusp, like a sharp point in your graph. The next one is if you have a limit that does not exist. So in this case, the left-handed limit did not equal the right-handed limit. And the last case is when you have a vertical tangent line. So we say then, to summarize everything we just talked about, for a derivative to exist, a function must be smooth, not smooth. Erase that. Smooth and continuous. Okay, continuous, again. Whoa, that's weird. Whoa, why did it just undo it? Holy cow. There we go. Smooth, meaning it doesn't have a cusp, right? It's just a smooth curve or smooth line. And then, you guys, my dog is so annoying. Hang on, I have to let her out of the room. And then, continuous, meaning it doesn't have a discontinuity, okay? So those are the two things. For a derivative to exist, a function must be smooth and continuous. The other thing that I want to point out that's super important is that if your function is differentiable everywhere, that implies continuity. Okay? Differentiability implies continuity. So again, go back to this definition of a function we talked about all the way up here. Okay? For a derivative to exist, you must have a limit from the left side equaling the right side. Okay? And a continuous function means that the value of your limit is equal to the value of your function at that point. So those things have to happen for a derivative to exist. So for example, if you know you have a derivative, you know your function's continuous. Okay, it's not the other way around. If your function's continuous, you could not have a derivative, like example 1 and example 2. Those are both continuous functions that don't have derivatives everywhere. But if you can find a derivative everywhere, you will always have a continuous function. Make sure you guys write down any questions you have, and I will see you in class later this week.